Hello everyone, this is Divakar Pandey. Today I'm going to discuss about the electric potential and capacitance. This is the new chapter of class 12 physics, and I will cover every topic from the NCERT book. So look at the whiteboard. Now, I am going to find the relation between electric field and electric potential. So, the topic is electric field and electric potential. Let us now show how the potential difference between 2 points is related to the electric intensity. You can say, I am going to derive what is the relation between electric field and electric potential. For that, let us consider 2 points A and B. Suppose that here it is point A and here it is point B. Lies very small distance dr. Suppose that initially the test charge q naught is at A, and suppose that the electric field generated by the point charge is E. Here it is the vector E. Now, the force acting on the test charge q naught, which is light at point A, the force acting on the test charge which is lies at point A is F is equal to q naught E. Now, we have to find the work done to bring the charge, that is the test charge, from point A to B against the electric field E. Suppose the test charge A is moving the small distance dr against the electric field E, so work done will be negative. Suppose that here it is equation number 1. So the work done in moving the test charge from A to point B will be dw is equal to f dr. Here this is the negative sign. Negative sign shows that the motion of the test charge is against of the electric field E. So dw is equal to minus f dr. This is equal to, the value of f is given, q naught E. So we can write minus q naught E and dr. You can say here it is from first. Now dw upon q naught. Now transfer q naught to the left side. So dw upon q naught is equal to minus E dr. Since V is equal to W upon Q naught, so dV is equal to dW upon Q naught. By using this relation over here, we get dV is equal to minus E dr. So E is equal to minus dV upon dr. Here this is the required relation between the electric field and potential. Here dV upon dr is known as potential gradient. Potential gradient, and it is defined as rate of change of potential with a distance. In other words, you can define the electric field can be defined as the negative of potential gradient, and from this relation you can easily find the unit of electric field. Electric field unit here it is potential, R is distance, so it is volt per meter. Okay. Now come to the next topic, that is potential difference and line integral of electric field. So the topic is potential difference and line integral of electric field. Let us consider 2 points A and B. Here it is the point A, and suppose that here it is the point B. Suppose that these 2 points A and B lies in an electric field, E. Now join A to B and take 2 points P and P dash on this line. Suppose that the potential difference between these 2 points P and P dash is dV, and suppose PP dash is equal to dl. In case suppose that it is the vector quantity, so PP dash is equal to dl. Here it is the displacement dl. Now here it is dl, and suppose that the PP dash, this line, makes an angle theta with the electric field E. Suppose that the potential at the point A is VA and the potential at point B is VB. Then from E is equal to minus dV upon dr, by using this relation we can write dV is equal to E dot dl. Here it is minus. Why here it is the scalar product? Why here it is the dot product? Because V is potential, so here the sign will be the dot product. Since the potential at A is VA and the potential at B is VB, so the total potential can be calculated by integrating dV. So integrate both sides. Here it is minus. Here at point A potential is VA and at point B potential is VB. Now integrate it. The integration of dV is V. Here the lower limit is VA and upper limit is VB minus. Here it is A to B E dot dl. Now V is equal to VB, here it is upper limit, minus V is equal to VA, it is the lower limit. V minus VA is equal to minus integration of A to B E dot dl. Here A to B E dot dl is called the line integral of electric field. Here it is the line integral of electric field E along the path AB. Now the electric potential difference between 2 points A and B in an electric field is equal to the negative of the line integral of the electric field from the point A to B. So you can define the electric potential difference between point A and B is equal to the negative of the line integral of the electric field from the point A to B by using this relation. Now in case suppose that the point A lies at infinity, if the point A lies at infinity, then therefore potential at A will be 0. So we can write this relation VB minus 0 is equal to minus A to B E dot dl. So we can write VB is equal to minus A to B E dot dl. Here from this equation, electric potential at point B in electric field is defined as the negative of the line integral of the electric field intensity E from a point infinity away from all charge, giving rise to the electric field to that point. So here this is the very important relation, VB is equal to minus A to B E dot dl. Now this is the potential difference and line integral of electric field. Now next topic is work done in moving a test charge along a closed path in an electric field, that is conservative nature of the electric field. So the topic is work done in moving a test charge along a closed path in an electric field. You can say conservative nature of the electric field. Let us consider a closed path APB P dash A. Here this is the closed path APB P dash A. Suppose that here this is the path, A P B A P B P dash A. In an electric field E, suppose that the electric field is E. Here the electric field is given. Here this is the electric field E. Suppose that the potential at point A is VA and the potential at point B is VB. Now, if WAB is the work done in moving a test charge Q naught, suppose the test charge is Q naught from A to B. Now, here WAB is the work done to move the test charge Q naught from point A to B. So, from the relation V is equal to minus A to B E dot dl, we can write WAB is equal to minus A to B integral of A to B E dot dl, and this can be written as Q naught VB minus VA, as we know that V is equal to W upon Q naught. So, W is equal to Q naught into V. Here it is the Q naught and here it is the potential difference. So, VB minus V is the potential difference between point A and B, and here it is W. So, work done from A to B, that is WAB is equal to Q naught, and you can write WAB is equal to Q naught, and here V is the potential difference. So, potential difference VB minus VA. So, by using this relation, what we get? WAB is equal to minus A to B dot dl, and this is equal to Q naught VB minus VA. Suppose that equation number 1. Now, we have to calculate the amount of work done in moving a unit charge from B to A along the path BP dash A, along this path BP dash A. So, the work done will be WBA is equal to along the path B to A, WBA is equal to minus B to A E dot dl, and this can be written as Q naught VA minus VB. Suppose that is equation number 2. Now, total work done in moving a test charge along a closed path from A to B and B to A. So, total work done is equal to WAB and plus WBA, and this is equal to WAB is given minus A to B E dot dl plus and plus minus minus, here it is the minus B to A E dot dl, and this is equal to, here it is Q naught and here it is Q naught. Q naught is common, so we can write VB minus VA and plus VA minus VB. By adding question first and second, what we get? Q naught VB VB cancel and VA VA cancel. Here it is 0. So, this is equal to 0. So, the total work done W is equal to 0. From this relation, it is clear that the total work done in moving a test charge along a closed path in an electric field is 0. Here this is the conservative field. Now, come to the next topic, potential at a point due to a system of charge. The topic is potential at a point due to a system of charge. Here it is the page number 4. So to calculate the potential at a point due to a number of charges, what you have to do? We have to apply the superposition principle. What is the superposition principle? Superposition principle means the potential at a point due to a number of charges is the algebraic sum of the potentials at that point due to each of these charges. Got it? This is the principle, superposition principle. So for find the potential at a point due to a system of charges, what you have to do? We have to apply the principle of superposition, or you can say superposition principle. Got it? For that, let us consider there is n charge q1, q2, q3 dot dot dot. Here there is n charge qn, and we have to calculate the potential at P due to these charges. So what you have to do? We have to apply the principle of superposition. Suppose that the distance of the point P from the charge q1 is r1, from q2 is r2, from q3 is r3, and from qn is rn. Then the potential at this point P due to these charges will be V is equal to V1, that the potential due to Q1, V2 the potential due to V2, Q2, and here it is V3 potential due to Q3, and finally Vn potential due to Qn. Here this is the algebraic sum. Algebraic sum means if the charge is positive, if here it is positive charge, then here there will be the sign will be positive, and in case if there is negative charge, the sign will be negative. If positive and negative both charges are there, so what we have to do? We use positive and negative sign both. Now we know that the electric potential due to point charge is V is equal to K Q upon R. Here R is the distance, Q is the charge. So by using this concept, what we get? V is equal to V1. V1 means potential due to charge Q1. So here it is K Q1 upon R1. By Q2, K Q2 by R2. Similarly, from Qn, here it is K Qn upon Ra. This is equal to, we can write it V is equal to sigma Vi, where I is equal to 1 to n, and this can be written as sigma K is outside, here it is the constant, and here it is Qi upon Ri, and here I is equal to 1 to n. The whole of K is given 1 upon 4 pi epsilon naught. So we can write sigma I is equal to 1 to n Qi upon Ri, and here it is V. So Vi is the potential. Got it? Vi is the potential at point P produced by the charge Qi. Vi is the potential at point P produced by the charge Qi, which is at a distance Ri from point P. The potential, unlike field strength, is a scalar quantity. Hence a single or a simple algebraic addition given by equation first is possible. Suppose that here it is equation number 1. So the potential at a point due to a system of charges V is equal to 1 upon 4 pi epsilon naught, sigma is equal to 1, and Qi upon Ri.